Okay, let's get started. In this quick MATLAB session, we will try to complete the inventory problem in MATLAB. So first, let's define the parameters. C0, let it be 750. This is the fixed cost. Fixed cost of orders. C1 is the variable cost of of orders. Variable cost of orders. This is the product price. Let it be 1. Just to keep things as simple as possible. This is product price. Beta, of course, this is the discount factor. And theta, which is 0.75. This is the shock distribution parameter. Okay. Next step, computed parameters. This is B1 and B2 in the exercise. We will use the formulas we derived in the exercise. So this is theta over 1 minus theta times beta. Okay, so this is the first computed parameter, and B2 on this ground, this is B1 times P over 1 minus beta times B1. Okay, that's nice. We need to define the initial stock. This is an arbitrary number, let it be 50. Okay, here we can take a section break, and now as the next step we are defining the Markov chain. Markov chain of exogenous demand shock. Please note, for IID shock, set equal rows for the transition matrix P. Okay, so let's choose a length of the chain, a length for the chain. This is 1000. Length of the chain. As a next step, we will define a value vector that gives values that assigns values to the states. Okay. Okay, so that's nice. We need a vector of random numbers. As you may remember, in the previous exercise, we worked out a possible MATLAB code for defining a Markov chain, and if so, you remember that this is the random, this vector of random numbers is the basis, on the basis of which we can define a Markov chain. Now we need another vector of the same length. This is the initial Markov chain, which we are going to overwrite. Okay, here as a next step we give a starting value for the Markov chain. Let it be 1. It could be 0 too. Starting value for the Markov chain. And as a next step, we are inputting the starting value into the Markov chain. Alright. And now we are defining the transition matrix. This is very simple. Please note we have IID shocks, so we have equal rows in the transition matrix. This is how we define the transition matrix or the Markov matrix. Okay, here we go. And now, as a next step, we will actually generate the Markov chain with the given values if we are following the steps we established previously. So if the value in the previous stage was 1, then we work with probabilities. We work with the probabilities in the first row of the transition matrix, and here come the probabilities. If this is lower than or equal to P11, then the next value in the Markov chain is the same. Else, if not, then the next value in the Markov chain is 0. Okay, and let's call into play the second row of the Markov matrix. I minus 1, if it's equal to 0, we are calling to play the probabilities in the second row of the Markov matrix. Okay. And this is the point where we refer to the random numbers. This is the reason why I told you that we need random numbers which we can force into a probability distribution we have just defined. So if this random number is lower than or equal to the probability in the second row of P21, then Mi is 1, else the next value in the Markov chain is 0. And we are closing everything, and here we can take, and we should, to keep things clear, we should take a section break. We can run what we already have. The next step is to find the optimal stock, capital S. We need another maximum number of iterations. It can be a huge number. This is the maximum number of iterations, and we are going to use the equation, inequality actually, from the exercise what we derived on paper with pencil. So this is the equation by which we are supposed to find S, capital S, the optimum capital stock, times beta times B1 J plus 1 times C0 plus C1 times J over 1 minus beta times B1 and the J minus C1. So this is the equation on the basis of which we are supposed to find the optimum capital stock. So where this equation, okay, before saying anything, we need another row in this matrix in which we collect the indices, okay, in the iteration. So here we are collecting the indices, and please remember, if this inequality on the basis of which we define the first row of matrix S becomes negative, then we can stop. And then we found the optimum capital stock. All right. here I forgot to start the for loop. My fault. So this is K. Okay, everything's clear. So we start a for loop, an iteration. You will see that the optimum capital stock inventory, sorry, not capital, inventory is so here we have S, and you can see it's a decreasing sequence, and at the point it becomes negative. Then we stop, and in the second row, by the second row of the matrix where we collected the indices from the key inequality, this is 38, so under these assumptions 38 is the optimum inventory. So we are almost ready. Let's take another section break and let's model the optimal behavior, which means that we will generate a series of inventory. Okay, so we create another for loop. If in the previous stage, in the previous period, the stock was 0, then in the current period we place the order and we face the demand shock. So we jump to the optimal inventory or optimal inventory -1, depending on the shock. If the stock previous period was not 0, then we proceed according to the stock and the demand shock until we reach the critical value where an order must be placed. Okay, let's run this section. Everything seems to be alright, and there is only one thing to do. Let's visualize the optimum behavior. So simply we will plot vector x in which we collect the stock in each period. So this is optimal stock following an SS policy. Okay, this is the title. Period. And stock. So here we are going to have, yep, it's very nice. So we can see that we reach the critical level, then we go back to the optimum inventory, sometimes optimum stock -1, sometimes the optimum stock, depending on the demand shock in each period. So that's all for today.